the last part of this chapter involves looking at something relatively straightforward, something which we have looked at before in terms of algebra, and that is, if you're given a function f of x, what is the inverse function to f of x? Okay. Now I'm going to start this chapter by saying that it follows on from where we finished in the last day's lesson. Inverse functions can only be created if the original function was bijective. Now, what does that mean? Can you remember what bijective means? Take a moment to think. What does bijective mean? It means one-to-one relationship between the values in the domain and the values in the range, but also it means that every value in your codomain is the range. So therefore, one-to-one is a unique one-to-one relationship. And then we say and onto, which means every value of your codomain is used as an output. Okay, so that's just to bring back what bijective means. But if the function is not bijective, then it can't have an inverse. Now that's a nice little shortcut. If somebody says to you, test and see, can this have an inverse? If they don't ask you to get the inverse, but they ask you to test, you're just going to test for bijectivity. And we'll come on to questions like that in a moment. So the key thing to remember is that functions that are bijective have inverses. Okay, if they're just injective or just surjective, they don't have an inverse. Inverse functions, such as f minus 1 of x, simply undo the action of the function f of x. What does that mean? Okay, here's a function. F of x equals the square root of x. Okay, now, what function would undo the square root? And the answer is the square. Okay, so therefore we could say the following. The inverse function to that would be x squared. So that when these two meet, here's what happens. You bring them together and you get the square root of x squared. And obviously you know what happens in that case. The functions cancel one another and they leave you with the original value of x intact. Okay, so that's just an example of where you have a function f of x and an inverse function. Now you'll notice I wrote that minus 1. That's the symbol we use as a power for the inverse function. All right, and what it basically means is, for want of a better term, it's turned upside down. Okay, if I was to ask you what's the inverse of 3/4, you'd say 4 over 3, because you're taking a fraction, turning it upside down. But in this case here, when we're inverting functions, it's a little easier. You simply manipulate the formula to get x on its own. Okay, and I'll do an example of that now in a moment and show you exactly where we get this thing from. So the inverse function is always given the power minus 1. So if f of x is the original function, f minus 1 of x is its inverse. Okay, and just keep that in mind. The minus 1 means the inverse. To find an inverse function, manipulate the formula. Now, we've done this already as a standalone exercise where I gave you functions and I said, look, make A the subject, or write this in terms of B, or write this in terms of Z. That's when we were manipulating functions. If you can't remember manipulations, pause now, go back to your book, look up manipulation of formulae, do a few of them, get the idea back in your head, and then come back for the inverse functions, because this is basically the same type of exercise. When we've manipulated, now we're going to end up being given a function, say y equals blah, 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 blah in x. Okay. When we manipulate, you're going to end up x equals blah, blah, blah in y. Now, there are no functions x equals blah, blah, blah in y. So the last thing we do is we switch the position of the variables. So when you do your manipulation and you get your x equals blah, blah, blah y, you switch the x's and the y's so that it takes on the proper form of the function. And lastly then, you simply put the power of minus 1 over the name of the function. If it was f of x in the beginning, it'll be f minus 1 of x now. If it was g of x in the beginning, it'll be g minus 1 of x now, and so on. Okay, best thing, a worked example. Find the inverse function of g as defined as follows. So here we've got a function. G of x is this. Now, I'm looking here at the domain and the range, okay? And the key thing I want you to remember is this. If a function is working within a given domain and range, its inverse will work in the same place. Because they're working in the same space and basically undoing one another, they are mapped by the same values, if you want to put it that way, in relation to your domain and your range. So they're not going to change. So I'm not going to worry about that. So you don't have to worry about this part. But what you do have to worry about is that you want to find the inverse function. Now, what I'm going to do, just shorthand, g of x. Let's write that down. What is it equal to? 2 times x minus 3 to be squared minus 5. Now, the name of the function, g of x, h of f, f of x, whatever you call it, that's just another way to represent y. So take your g of x or your f of x or your h of x, whatever they give you, and just call it y. Y equals 2 times x minus 3 to be squared minus 5. And your job is to isolate x. Now we have enough tools in our arsenal at this stage to be able to do that, okay? So let's take a look. That's what I want to isolate. That's my focus of attention. So everything else that's not x has to be eliminated from the right hand side. And the first thing I'm going to do is I'm going to eliminate minus 5 by adding plus 5 to both sides. So y plus 5 equals 2x minus 3 to be squared minus 5 plus 5, which cancels. See? So that's your minus 5 taken care of. The next thing I'm going to do is I'm going to get rid of a 2 that multiplies over here, which means I'm going to divide by 2 on both sides. And if I divide by 2 on both sides, I get y plus 5 over 2 is equal to x minus 3 to be squared. Now, the next thing to go is the square. So in order to get rid of a square, we get a square root on both sides. And please don't forget that because you're dealing with an equation, whatever you do on the right hand side, you've got to do on the left hand side. Or more generally, whatever you do on one side, you've got to do to the other to keep the equality, to keep it balanced. So what do we end up with then? We end up with now the square root of y plus 5 over 2 is equal to x minus 3. And the last step to get x on its own is to add 3 to both sides. So we get the square root of y plus 5 over 2 plus 3 is equal to x minus 3 plus 3, which cancels, and that is your finished manipulation. But it is not the proper form of the inverse function. Remember what I told you? Manipulate, get x on its own, and then you have to swap the position of x and y. So in other words, what I now do is I rewrite this equation with the x and the y's in each other's places. So it becomes the square root of x plus 5 over 2 plus 3 is equal to y. Now what's y? Y is the inverse function. So the last thing we do is we replace y with f minus 1 of x. And that's equal to the square root of x plus 5 over 2 plus 3. And that is your inverse function. Okay, so it's just an exercise in manipulation. That's all it is. Now I have this thing printed out here for you, so I'm just going to go through it very quickly. We manipulate 2 times x minus 3 squared minus 5. Manipulate it fully to get x on its own, and that ends up giving us y plus 5, square root of y plus 5 over 2, and that's equal to x. Okay. Now switch to actually there's a 3 missing there. That's my apologies. So there's a 3 to go in there, and that's, what have you got? Minus 3, so that's a plus 3. There should be a plus 3 in there as well. That's me too fast typing things up and not thinking hard enough. And then obviously that's plus 3 in there as well. Okay, so we manipulate, and this is what we end up with. Okay, the square root of y plus 5 over 2 plus 3 equals x. Now, swap the position of x and y. That's the key thing. Swap these two around. And when you swap them around, you get x plus 5 over 2 plus 3 equals y. And finally, replace the y with the inverse function symbol, f minus 1 of x. Okay, notice, and we set it down here and it says it in your book somewhere, the inverse function works in the same domain and codomain. So don't get caught up about where you're working, all right? Just get caught up about the algebra. Take the function, set it equal to y, manipulate the function until you get x on its own, change spaces with the letters, put them into each other's places, and then at the last step, take the y and replace it with f minus 1 of x. Okay, here's another one. Investigate if the following function has an inverse. Now, they're not asking me to find the inverse. They're just asking me to investigate. That's the key word. Investigate. Does it have an inverse? And the answer is it only has an inverse. It has an inverse if the function f of x is bijective. Now, what does that mean? If this function here is a one-to-one relationship uniquely between domain values and range values, and secondly, if your range is your codomain, it means all values in your codomain become part of your range, then it's bijective. So all I've got to do here is test for bijectivity and test and see, does it have both injectivity and surjectivity? So the first thing I'm going to do here is I'm going to take a look at my domain and my range, because that's important, okay? My domain and my codomain, I should say. So I'm working from minus pi over 2 to pi over 2. And then I'm going from minus 1 to plus 1 on the y-axis. So let's just take a look at it. This is what we have, something like this. So we're going from plus 1 to minus 1. And then we're also going from minus pi over 2, which is here, to plus pi over 2. Now, what does a sine function do? A sine function begins at 0 and moves up to 1 at the point pi over 2. Okay, just keep that in mind. So we've got a point up here, like that. Pi over 2 is 1. Minus pi over 2, therefore, will be minus 1. So with a graph that looks like this. That's it. Okay. Now, here's your job. Taking the domain from minus pi over 2 there to plus pi over 2 here. We're only working within those two boundaries. If I do the horizontal line test, what do I notice? Taking the horizontal line test, are all the values, and by the way, we're also only working between minus 1 on the y-axis and plus 1 on the y-axis. So we're working in this window, okay? Now, if you move a horizontal line up and down inside that window, what do you notice? You will only ever cut the graph once. Good. So there's a one-to-one relationship. So it is injective. Okay. Now, is it surjective? That's what we want to test next. Well, we're only allowed to have values in my codomain from minus 1 to 1. So we're only moving from here to here. Now, are all those values that are related to the function as drawn? And the answer is yes. No matter what value you take between minus 1 and 1, it will have a corresponding value on the graph. Therefore, it is surjective. And if it is both of these, then it is bijective. And if it's bijective, it has an inverse. Okay, that's it. That's what you do. So you test for your bijectivity. So it's very important, again, not only do you have to know how to manipulate algebraic equations, you've got to also be able to understand injective, surjective, and bijective functions. Okay, last one. Page 166, question 16. The function h works in the domain of real values towards a codomain of only positive reals. Okay, where my domain x becomes my range 2 to the power of x. Find h to the minus 1, the inverse of h. Now, what am I going to do here? What's the shorthand? H of x equals 2 to the x. Write down the shorthand. H of x equals 2 to the x. Okay. How do I get this down to y? Don't forget h of x is another name for y. Okay, so there we go. Now, I have to invert this. Okay. This is an this is an indice with base 2 and index x. My job is to get rid of the base 2. And we're going to find out in the next chapter. Right, the next chapter is going to involve logs and indices. But what we notice here is to try and get rid of a base 2, I've got to bring in log with a base 2. Now, we've done functions already before, so we should have some idea in terms of logarithmic functions how these things operate. So here's what I'm going to do. Log to the base 2 of y is equal to log to the base 2 of 2 to the x. Now, we met this before. If the base of the log and the base of the index are the same, then they'll cancel, giving me log to the base 2 of y is equal to x. Okay, that's my manipulation taken care of. That's step 1. Step 2, change positions of x and y. Log to the base 2 of x equals y. And the final thing to do then is to replace your y with f minus 1 of x. And that is your inverse function. Okay. Now, the next part. Verify that the function in the invert function is the same as the inverted function placed into the function itself. Okay, so let's just think about that. Where's the original function? There's the original h of x, okay? And down here is the h minus 1 of x, if you want to put it that way. They didn't use an f, sure they didn't. It was a h they used. Let me just change that letter for you, because it's h. So there's h minus 1 of x. Okay, what does the first thing tell me to do? The first thing tells me to take h of x and bring it into the inverse. So in other words, bring 2 to the power of x into this one here. Okay, so h minus 1 of h of x. What am I going to do? Take h of x into h minus 1. So we're going to put 2 to the power of x, which is h of x, into log to the base 2. And what happens there? The log has base 2, the index has base 2, so they will cancel. See that? They'll cancel, leaving you with x. And the next one is h of h minus 1 of x. Now this time we're starting with the inverse, which is log to the base 2 of x. And what do I want to do with it? Put it into h. So what's h? Base 2. So it's 2 to the x. So therefore, again, the base of the index is 2, the base of the log is 2, they cancel, leaving you with x. So verify that h to the minus 1 of h of x is equal to h of h minus 1 of x by telling me x equals x is now verified. That's it. Okay. And finally then, the graph of inverse functions. This couldn't be easier. We're ending up in a very easy section in this case. And here's all I want you to remember. The graph of an inverse function is the mirror image of that graph through the line y equals x. Okay, now that's the key thing. So basically all they're ever going to ask you to do is to draw or sketch the inverse function to a given graph. Okay, so let's take this one here. Sketch the inverse of the function 0 to infinity. There's your domain. That's fine. There's your codomain. There is your domain values, and there is your range. Okay, on the graph below. Now look, when you're told to sketch the inverse, you have to worry about nothing. The only thing I would suggest you do is you put in the line y equals x. Now let me see if I can do this in a different color. I don't know whether I can or not. Oh, I can. Let's do it in blue. Okay, so what's the line y equals x? So my advice number 1, draw y equals x. That means put a point at 0, 0, 1, 1, 2, 2. So draw that line like that. Okay, so there's y equals x. Now, inverse graphs are symmetrical around that line. That acts like a mirror, which means, let me go back to red, that the inverse of this function is going to be on the other side perfectly symmetrical to it. So all I want to do here is measure that, go perpendicularly there and go the same distance the other side. See that? To there. Same thing here, and then the same thing here. Something like this. So you end up getting the following. And there is f minus 1 of x. It's that simple. That's all you've got to do. You take the line y equals x, you draw that first. Then you measure a couple of distances between the original graph and that line, that mirror line, that symmetrical line, and you simply then find out where the other one is, and you draw it symmetrically to the previous function. Now, because it said sketch, you're allowed a kind of a wide margin of error. As long as it looks like a mirror image of the original, you're fine. If it looks like something mad, then you're out. You get no marks whatsoever. So there you go. And see, I've got exactly the same thing. Now, they measured a couple of points that I measured. There's one. Measure another one here, maybe. Measure another one here. And then just make sure the distances are the same either side. Theirs is a little bit better than mine. Okay. Next one. Sketch the inverse of the following functions. F of x equals that. So there it is. There's the function f. Okay. Now, where's f minus 1? Step number 1, draw in the line y equals x. So go to 0, 0, go to 1, 1, go to 2, 2, go to 3, 3, etc. Okay, and draw that line in like that, because that's your symmetry line, like that. So that's the line y equals x. That's your mirror. Okay. Now just take a few points either side of these lines. So let's take, for example, that's at 0. So there. Let's take this one here. Now you're drawing perpendicular, okay? It's a hard thing to do when you're dealing with a machine like this, but they're roughly there, okay? Then you have say, this point here, you're going to get something like this. It's going to go something like that. Okay, and as long as it looks symmetrical, now you have to show that you're measuring. So you're going to measure the distance between, say, that point and this one here and go the same distance the other side. You're going to measure the distance between that one and this point here, and then go the same distance the other side, and so on. So you're trying to get a mirror image of what the original graph was through the line y equals x. So therefore, if that's the original function f, and that's the line y equals x, well then this is f minus 1. It's the inverse graph. And that's it. Finished. So what I'm going to do is I'm going to leave you these questions here to do. That, of course, should be question 3, 5, 10, 12, 17. There's no question 1117. It's 12 and 17. And basically all they're asking you to do are manipulations. Okay? Manipulate. This one here is asking you to check and see, is there a bijectivity ongoing in this function? If there is, then it's going to have an inverse. And the last couple of questions then, like question 10, it's just asking you something very simple. Draw the inverse of the following function. Sketch the inverse. So put in the line y equals x, and then draw symmetrically on the other side of line y equals x as if it was a mirror. Okay, so I'm going to leave you with those to do. We will have a live class to come back and look at these carefully. Then I'm going to take some questions maybe from past papers before I set an exam on this thing, that on functions, that we want to do a fairly comprehensive exam because it is quite a long chapter before we move into the next chapter, which will be logs and indices.